Good evening, Doctor. We are from Group 5 and we are going to present about our project on load flow. So I'm T. Jingyuan.
And I'm Song
I'm Chris Ang.
So before we start the simulation, let me do some simple introduction about our project. So basically this project is we need to construct a circuit on power flow, on power wall to observe the power flow and also the data in Excel. So let's start from case 1. So this is the circuit that we constructed in case 1. You can check the parameters, and for the parameters, you need to do the calculation, and it's in our report. So let's check this is the bus, and this is the transformer. You can see that the reactance for a transformer is 0.1 because we take the base at 100 M. So the basis has not changes, so we no need to change for the transformer 1. So and then this is the transmission line. So for transmission line, we need to calculate the R, the X, and also the B. So we can check the calculation later. And also for the transformer, we need to check about the fault. So this is 0.1. The generator, this is 0.12, 0.14, and 0.05 because the base is the same, it doesn't change. So when we make sure that all parameter is correct, then we can run the circuit. So you can see that in case 1, there will be an overflow at transformer 1, which is 105%, because you can observe here, it is 104.83 MVA. So this overflow in the circuit is not good because it consumes power and it will cause the power wastage. So we will try to resolve this situation in case 2. And you can also obtain the output for case 1 here. The model explorer can get the branches, generators, and also the buses. All right, so now we start the case 2. For case 2, if you want to resolve the power flow, you will need to, our solution is to insert a switch shunt at the bus 4 because we also need to increase the voltage at bus 4. So for the MVAR, we don't know the value, so we just use try and error. Let's say we put 40. All right, so we run it again. So you can see that the overflow has been resolved, but the voltage here is still not our desired value. So the desired value should be 221.58. So we try to increase the MVR here. Let's say we put 43. So you can see that the voltage at bus 4 increases, and we try to increase it again. Okay, still a bit. All right, so it's 221.57 now. Okay, it's the same. So the value we set for the shunt capacitor is 44.4, and the actual is 41.2, because due to some power loss in the circuit. So this is the complete circuit for case 2, and we need to get the data again, the output. So these branches, generators. You can see that the MVAR for the generator 1 has decreased. is the Q value, which is good for the circuit because we don't need Q in this case. And we check the buses. All right, so let me pass it to my member so we can explain about the situation in case 1 and case 2.
So for the calculation in part 1, we will calculate the generator reactant, transformer reactant, and transmission line impedance in per units. So for the transmission line impedance, as here we will get this one R and X. So by according this calculation, we will get transmission line impedance in per unit. For the according this, we will continue our calculation for the B. Then for case 1, this one is the result. We get it to the input data for buses from figure 2, as you can see here, and the output data for buses. So after that, the figure 4 is input data for transformer and transmission lines, and the figure 5 is the output data for transformer and transmission line. And the last two is the generator. This one is input and this one is output. So in our discussions, in case 1, the value of base V and S are set to 13.8 kV and 100 mega respectively, and generator ones. This is the reference from which all the impedance, voltage, and load value are converted to per unit system for consistent across system component and to standardize the value in power walk simulators. The data of the circuit is obtained through the simulation and the data is explained to Excel. The result is displayed to figure 1 to figure 7 from just now I show. In the case an overload is observed in transformer 1 due to the apparent power exceeding rated capacity of MVA. This causes a low system efficiency caused by the large amount of reactant power generated by the generator. Reactive powers is created by the reactive components in AC systems like inductor and capacitor, where it helps maintain voltage stability. Excessive reactive power leads inefficiency. So for the excessive reactor power in the system can lead to undesirable voltage drops and increased power losses along the transmission line. Therefore, it is essential to minimize reactive power to exchange system performance and efficiency, which will carry out in the following cases.
For case 2, we need to suggest a method to increase the voltage magnitude at bus 4.5%. So to increase the voltage at bus 4.5%, a shunt capacitor is added, and the shunt capacitor is added because the capacitor provide the reactor power and provide a leading current to deduct the lagging current in the circuit. From figure 8, the voltage at bus 4 is increasing from 211.028 kilowatt to 221.569 kilowatt, which close to the expected value of 221.579 kilowatt. This means the suggestion of adding shunt capacitor is reliable. The shunt capacitor will deduct the reactor power demand on generator and able to maintain rate voltage on the load bus. In the conclusion, the simulation of the power simulator for each case has been successful. Done. Adding a shunt capacitor to the relevant bus can reduce the reactive power of the system. The power correction need a higher value of the reactor power by the shunt capacitor, reducing power loss during transmission, enhance system efficiency and reliability by minimizing reacting power and optimizing the network power flow. The overall performance of the system improves, ensuring a stable and dependent operation.